Level 1. Ancient intuition. Early civilizations like the ancient Greeks struggled with the concept of infinity. Infinity started not as a number but as a concept, something that has no end. In the 4th century BCE, Aristotle made the crucial distinction between what he called potential infinity and actual infinity. Potential infinity describes a process that has no end, for example counting 1, 2, 3, 4 and so on forever, whereas actual infinity describes a completed infinite quantity. Meaning it has no end, but also at the same time it is somehow completed. This idea was rejected by Aristotle because he thought it was paradoxical and impossible in reality. This philosophical stance dominated Western thought for nearly 2,000 years. Unfortunately for many 5-year-olds across the world, infinity isn't just the biggest number because it isn't actually a number. And before any 5-year-olds come at me with the, oh, but what about infinity plus 1? Didn't think about that one, did you? Well, actually I did. Infinity plus 1 also isn't a number because infinity can't be manipulated like numbers like 5 or 10. Instead, infinity is a concept describing unboundedness. Even today in standard arithmetic, infinity is not a real number, so statements such as infinity plus 1 equals infinity are not true in the usual sense, but are sometimes used as shorthands when working with limits, for example. These statements both make sense and also don't make sense, and if that confuses you, then let me remind you that this is only level 1 and it only goes downhill from here. Level 2. Paradoxes of infinity. In the 5th century BCE, a G called Zeno of Elea started bamboozling the mandem with his paradoxes about infinity. His most famous example, Achilles and the tortoise, shows that to reach any destination, you must first go halfway there, and then halfway again, and then halfway again, and so on infinitely. This suggests motion is impossible because it requires completing infinitely many steps. These paradoxes forced mathematicians to confront the idea that infinite processes can produce finite results. But mathematicians were still salty, and this tension wasn't resolved until calculus was invented in the 17th century by Isaac Newton. And if anyone says that it was actually Leibniz who invented calculus, ignore them because that's just German propaganda. Level 3. Calculus and controlled infinity. In the 17th century, Gottfried Wilhelm Leibniz invented calculus, giving mathematicians a way to actually deal with infinite processes with mathematical rigor. The central idea is limits. Instead of completing infinitely many steps, you approach a value arbitrarily closely. For example, we can say that the infinite series 1/2 plus a quarter plus an eighth plus a 16th and so on converges to 1 arbitrarily closely. This shows that infinitely many terms can sum to a finite result. And if you or someone you know wants to learn calculus, then Brilliant has an all-new calculus course. Brilliant is ideal for grades 5 through 12, and they've just revamped their website with new courses and features. The truth is, educational standards are lower than ever, and while one-to-one tutoring is an excellent alternative, it's often expensive and logistically difficult. That is why Brilliant launched a new AI tutor to deliver personalized learning for struggling students.
3 people know a joke, and the count doubles every day. Build the expression for day 2.
Okay, day 2. So 2, 2, 2. Help me, I don't know what to do.
Koji doesn't just give away the answer, he asks questions and guides the student to find the answer themselves.
You're getting the doubling right, but how many people started with the joke on day 0?
Oh, 3 people. Okay. Yeah!
That's right.
Yeah! Yeah!
I really like how Koji has essentially infinite patience because any other teacher would have just crashed out by this point. I wish I had this when I was a student because I was always that kid who was too scared to ask the teacher a question, leading to gaps in my knowledge that I had to fill in myself later. Click the link in the description or scan the QR code on screen to get started with Brilliant's tutor for free. You can also upgrade to premium to unlock all courses, and right now the unqualified tutor viewers get 20% off of an annual premium subscription at brilliant.org/the-unqualified-tutor. By the 19th century, Augustin Louis Cauchy and Karl Weierstrass formalized limits using epsilon delta definitions. Let f of x be a function defined near a but not necessarily a. We say that the limit of f of x as x approaches a is L if for every epsilon greater than 0 there exists delta greater than 0, such that whenever 0 is less than mod of x minus a less than delta, then mod of f of x minus L is less than epsilon. And if you can't repeat this definition off by heart, then according to university, you don't deserve a maths degree. degree. Level 4, different sizes of infinity. George Cantor proved that not all infinities are equal. He introduced set theory and showed that different sets can have different cardinalities or sizes. For example, the set of natural numbers 1, 2, 3 and so on is infinite, but so is the set of real numbers between 0 and 1. If we assume that the set of natural numbers has the same cardinality or size as the set of real numbers between 0 and 1, then that implies that for each real number between 0 and 1, we can pair it with a natural number. But let's assume we do this, so now we have an infinite list of numbers between 0 and 1, then we can construct a new number by simply saying that the nth new digit is equal to 5 if the nth digit of the nth number is not equal to 5, and the nth new digit is equal to 6 if it is equal to 5. So that means that this new number is not equal to the first number because it's different in the first digit, not equal to the second because it's different in the second digit, and so on. This is called Cantor's diagonal argument, and it proves that the real numbers are strictly more infinite than the natural numbers. Level 5, transfinite numbers and ordinals. But Cantor didn't stop there. He created arithmetic for infinities. He introduced transfinite numbers, which include cardinal numbers like aleph null, aleph 1, and so on, and ordinal numbers, which describe order types. Ordinal infinity goes beyond size and includes a structure. For example, omega represents the order type of the natural numbers. And unlike normal infinity, you can define omega plus 1, omega plus 2, and even omega times 2, but they behave differently than in finite arithmetic. David Hilbert popularized these ideas with Hilbert's Hotel, a thought experiment showing that a fully occupied infinite hotel can still accommodate more guests by just shifting the occupants around. This demonstrates that infinite sets behave fundamentally differently from finite ones. Level 6, infinity breaks logic. In the early 20th century, attempts to formalize all mathematics led to some surprising limitations. Kurt Gödel proved his incompleteness theorem in 1931, showing that any sufficiently powerful mathematical system cannot be both complete and consistent. There will always be true statements that cannot be proven. Infinity plays a key role here because these results rely on constructing statements about infinite sets and self-reference. At the same time, set theory encountered paradoxes, like Russell's paradox, for example, which asks if the set of all sets that don't contain themselves contains itself. The answer is both yes and no, and also neither, and also both at the same time. This shows that naive set theory breaks easily when dealing with infinities. This forced the development of axiomatic set theory, like for example Zumelo-Frein-Keil set theory, which attempted to eliminate these issues. Another major idea is the continuum hypothesis posed by Cantor, which asks if there is an infinity strictly between the number of integers and the number of real numbers. Paul Cohen and Kurt Gödel proved that this statement can neither be proven nor disproven from standard axioms, meaning that we will never know the answer, and we've proven that we will never know the answer. This is one of the first major examples of mathematical truth being undecidable. Level 7, modern infinity. Today, infinity is studied in multiple advanced frameworks which push beyond classical set theory. Large cardinal theory explores infinities far beyond aleph null, like for example inaccessible, measurable, and supercompact cardinals. These objects cannot be constructed explicitly, but can be studied through their properties. Category theory and higher category theory reinterpret mathematics in terms of relationships rather than elements, leading to new ways of thinking about infinite structures. Homopity type theory merges logic, topology, and computation, treating mathematical objects as spaces with infinite structure. Set theorists also study forcing, inner models, and independence results, studying whether different mathematical universes can exist depending on the chosen axioms. At this level, infinity is no longer just the size of something or a process, it becomes a landscape of mathematical possibilities. And the deepest insight is that infinity is not just a single concept, but an entire hierarchy of structures, some of which may never be understood. If you want to learn university maths but don't want to get into debt, then click the link in the description.